Hello, we are starting chapter 1 here. It is Introduction to the Differential Equations. The first section 1.1, we start with some background. You already have seen some differential equations in previous classes. And so what is a differential equation? Basically, it is an equation which contains derivatives. They can be ordinary derivatives or partial derivatives. So if you recall from Calc 2 and Calc 3 that d by dt, that is the differential operator. Such an operator is called an ordinary differential operator. And then if you have this symbol, partial by partial t, that's how we say it. So that is for the partial derivatives. So these are for the ordinary derivatives, and these are the partial derivatives. So we can have a differential equation with in ordinary derivative or partial derivatives. And actually many real life phenomena are depicted by these mathematical models involving differential equations. So what is this simple differential equation? Whenever you see the rate of change of something, so if you recall from again Calc 1 and Calc 2, the rate of change is d by, so for example dA by dx means the rate of change of a with respect to x. dy by dx means the rate of change of y with respect to x. So here we are taking the differential or the derivative of y, and we are differentiating it with respect to x. If we say dy by dt, it means we are differentiating y with respect to t. So here are some examples of these equations in real life. We know from the Newton's law of motion, or Newton's second law of motion, F is equal to ma. Means the force acting on an object of which has a mass denoted by m, and if body is moving at an acceleration a, then the force is equal to the mass times the acceleration. Now how do we represent an acceleration? If you recall, if u is the position function, then du by dt will be the velocity of the function, and d2u by dt2 means the second derivative of the position function, which means the first derivative of the velocity function. That will give us acceleration, a of t. So a of t is the second derivative of the position function. So we can plug in d2u by dt2 for a in the above equation, and so this became a differential equation. Some other examples are that dp by dt is equal to k times p. So this is a population growth equation, a differential equation. Why is it a differential equation? Because we see a derivative present on the side. Then another, in engineering, maybe you have seen an electric circuit equation where L, R, and C are, I think, inductance. One is inductance, one is capacitance, this one, and the R is the resistance. So in an electric circuit, you will often see an inductor, a capacitor, and a resistor. So that's how the equation of the electric circuit is. And then another one is a vibrating screen. So now notice here, this last one is the only one we see here with the partial derivatives. So that is a PDE. The rest of them are ordinary differential equations, ODE. So some terminology and classification. So what is an ordinary differential equation, which we often indicate by ODE? So it is an equation involving only the ordinary derivatives. And the partial DE is the equation involving the partial derivatives, like number 4 up there, that is the PDE. So this one is PDE. The rest of them are ODE. So what is a dependent variable? The quantity whose derivative is being calculated, that will be a dependent variable. And what are the independent variable or independent variables? There can be more than one. So these will be the variables with respect to which the derivative is being calculated. So for example, in the first equation over here, the independent variable is t and the dependent variable is u, because we are taking the derivative of u with respect to t. So t is independent, u is dependent. In the second equation here, so we are taking the derivative of p here, and with respect to what? T. So p is the dependent variable and t is the independent variable. Similarly, in 3, q, little q here, this is your dependent variable, because you see everywhere we are taking the derivative of the q, and the independent variable is t. In equation 4, so our dependent variable is u, because we are differentiating u, but now we have two independent variables. One is t and the other one is x. So we can have this situation where we have two independent variables, so more than one independent variables. Okay, so what is the order of a differential equation? It will be the largest derivative present in the differential equation. So for example, again going back, number 1, this is second order. So this is the order of this one is second. Okay, this is a second order differential equation. Number 2 is a first order differential equation. Why? Because the derivative is the first derivative present here. In the same way, number 3 is, I believe you guessed it, it is a second order differential equation, because the highest derivative is the second order derivative. Similarly, number 4 is a second order differential equation. Okay, the next thing is linear DE. So what is a linear DE? So we say a linear DE will be a differential equation of this form. Now it is hard to understand what is written here, but let me explain. Okay, so here this is the nth derivative, whatever n may be. It could be 100, it could be 2000, whatever. And then this is the one less, and then one less, and one less, and one less, and until we come to the first derivative here, and here it is showing the zeroth derivative. The zeroth derivative we say is the function itself, or whose derivatives are being used. So y is the quantity, the dependent variable, whose derivatives we have on this left side. And on the right side, we have another function which there is no y on this side. Notice on the right hand side. Okay, so there is no dependent variable on the right hand side. Now g of t could be 0, or g of t could be a function of t in this case. So since this is a complicated one, let's look at some simple ones. So first order linear differential equation will look like this. So a quantity, a function of t multiplied by the first derivative plus a function of t multiplied by the y, and then on the right hand side we can have the function only of t. Now these are called the coefficients of these terms, or of the function and its derivatives, and they should be so to be a linear ordinary differential equation, these functions, which are the coefficients, must be functions of the independent variable only. Okay, and the other thing we have to check for a linearity is that any derivative or the function itself, so y or any derivatives of y, must have the first power in the equation. Then it is called a linear differential equation. So the coefficients can have different names. So here I'm using P and Q. Here we are using A1 and A sub 0, which are coming from this long differential equation. Okay, the second order differential equation again can look like this. So a function of t multiplied by second derivative of y plus a function of t multiplied by the first derivative of y plus a function of t multiplied by y equals a function of t. And again we can have different names of the coefficients. Okay, so now what is this? This is the same equation as I have up here. So what is this? This is the nth order linear differential equation. Okay, so n can be anything, 3, 5, 8, 10, whatever you want. Okay, another names or some more vocabulary here. So this is a word which can be pronounced in different ways, but I think the correct pronunciation is something like homogeneous. So if g of t is equal to 0, so what is g of t? Remember, it is the function on the right side of the differential equation. So the quantity which was without the independent variable or its derivatives. So the quantity which is only the function of t. If that quantity is 0, then the differential equation is called homogeneous differential equation. And if the g of t is not 0, it is some function of t, then the differential equation is called non-homogeneous. So non-linear DE. So what is the non-linear DE? Of course, it is a DE that is not linear. So let us look at some examples. So look at this example here. So we see this is the second derivative of y and this is the first derivative of y. So these are to the first power, so okay. Now this is being multiplied by nothing, which means it is being multiplied by 1, which is okay. And this is being multiplied by x squared, so which is still okay because we can have function of the independent variable. And you can see independent variable here is x, dependent variable is y. Now the quantity here should be a function of the independent variable, which is q of x times the quantity y. But what we have here is y cubed, which we can think of as y squared times y. So this is the culprit. This is the function, or this is the expression which is making the equation non-linear. So we say this is non-linear, and the reason is because of this term. Okay, looking at the next example, number 2 here. So this one is fine. So we see the independent variable is t and the dependent variable is y. And then we should have quantity multiplied by the first derivative. But what is this quantity? This is a y. This is the dependent variable. So that is not correct. That is what makes it a non-linear equation. Last one here. So we have dy by dx, but wait a minute. This is the first derivative, dy by dx, and it is being raised to the second power. So that is what is making this a non-linear differential equation. Okay. So we can say that a differential equation is linear if the dependent variable and all its derivatives present in the equation appear with power 1. And also the coefficients of the dependent variable and its derivatives, whichever are coming in the equation, must be a constant or a function of the independent variable only. Okay, remember, a constant can be considered a function of any variable, whichever variable we are using in the equation. Okay, so let us see if we can figure out which differential equation is linear and which is not. and also which one is actually a ordinary differential equation and which one is a partial differential equation. Okay. So here, the first example, A. Also remember we have to indicate the independent variable, the dependent variable, and if the equation is an ordinary differential equation, we have to tell whether it is linear or non-linear. Okay, so looking at the first A, the example A here, we will first find out what is happening here. What type of derivatives are we taking? We are taking the ordinary derivative, so it is an ODE. Okay. The next thing we have to look for is the dependent and the independent variable. So you see here we are taking the derivative of x with respect to t. Okay. So what does it look like? This is the second derivative of x with respect to t. This is the first derivative of x with respect to t. This is the quantity x, so which fits our situation. So this looks like an ordinary differential equation which has the independent variable t. So independent variable is equal to t. Dependent variable is x, right? Okay, because look at the right hand side. We have a quantity which is a function of t only, which is allowed. Remember, we can have a function which is only depends on the independent variable. The next thing we have to check is what is the order of the equation. So we see this is a second order differential equation. Okay, the last thing, whether linear or non-linear, well, we see the first coefficient is 5, the second is 4, the third is 9 here. So, and the right hand side is a function of t. So it is a linear differential equation. Now looking at example B, we have partial derivatives appearing. So this is a PDE. What are the independent variable? The independent variable is, actually there are two of them because we are differentiating it with respect to r and also with respect to t. So the independent variables are t and r. The dependent variable is n because it is the derivatives of n are being taken. So in this case we have to tell the order. Well, the highest derivative is the second. So again this is a second order differential equation. But now in this one we cannot talk about linear or non-linear. So that's all we cannot tell. Looking at example C now. dp little p is equal to k times little p times parentheses, in parentheses we have uppercase p minus the lowercase p. So here it is mentioned that the k and the p are the constants. So what does it look like? On this side we have a quantity. If we distribute it, so we can write it like this: k little p big P minus k p p. Okay, if we move everything to the left side, or at least move the quantities which have the little p to the left side, well, both of them have the little p, so I move everything on the left side. What do I get? dp by t, remember we are taking the derivative of the little p, so minus k big P, because these are constants, time the little p, plus k little p square equal to 0. Oh, well, this is okay and this is fine, but what about this one? So this is giving us a square of the dependent variable. So that is what makes it a non-linear. Okay, so first thing, what is the order of this differential equation? First thing, this is an ODE. What is the order here? The order is the first order, because we are using only the first order differential equation. Although here we have a p square, okay? The square is on the, not the derivative, right? This is just the quantity, the dependent variable squared. But the derivative is the first derivative. The order of the differential equation depends on what is the highest derivative that we are taking. So it's a first order differential equation, and the independent variable is t. The dependent variable is little p. And is it linear? No, it is a non-linear equation. And because of the quantity, because of kp square, this term. Okay, this part D. So it's a 7d4y by dx4. So we are now talking about the fourth derivative here. And then on the right hand side, I see a function which depends on x only. Well, let's see. So from the left hand side, we notice that we have a ODE. Order is 4. The dependent variable, or first maybe talk about independent variable. So independent variable is x. Dependent variable is y. Okay, so what is the order? Order is 4. Okay, the next thing, is it linear or is it non-linear? Well, the coefficient of the derivative is 7, and we have this quantity which is only depending on the independent variable. So yes, this is a linear equation. Okay, so this is how we check whether it is linear or not. Okay, let's look at the second example. So here we are saying that we have to actually, depending on what is written here, we have to create or write a differential equation. Okay, so it's the first example said that rate of change of mass A of salt at time t. So rate of change, okay, of mass A of salt at time t. So what does that mean? The rate of change of A with respect to t. So how do we write it? dA by dt. So this is the rate of change of A with respect to t is proportional to the square of the mass of salt present at time t. Well, what is the mass of salt present at time t? It is denoted by the symbol A. So we are saying that dA by dt is proportional. So what does it mean to be proportional? Well, basically it means it is not exactly equal to, but it is equal to a multiple of the quantity. So which means we can write it as dA by dt is equal to k times, what? K times the square of the mass of the salt. So the mass of the salt is A, so we say A, Ka square. So this is what the differential equation will look like. So whenever it says proportional to, so what we do, we put equal to sign and we put a K here. So if it would say the rate of change of mass is equal to the square of the mass of salt, then we will just say dA by dt is equal to K, A square. But then we won't put a K. But K is coming, little k, because of the proportionality, and then K is a constant. Or we sometimes call it constant of proportionality. So how do we determine K? Well, that depends on what conditions or what information is given. But here we are just looking at, the question just asks us to create the differential equation. So we don't worry about how to find the K. Okay, the second one, the rate of change of temperature T of coffee at any time. So what are we talking about? The rate of change of the capital T with respect to the little t, where the capital T or the uppercase T is the temperature of coffee at any time, and the little t is the time, is denoting the time. So it says the rate of change of temperature T of coffee at time t is proportional. So remember, proportional means we will say equal to K times the difference between the temperature M of the air at the time t and the temperature of the coffee at time t. So this will be K times M minus the uppercase T, the temperature of coffee at the time t. So this is how the equation will look like. Okay, so that's section 1.1. So we got familiarized with some notation and some vocabulary, and now we will go to the second section and see what is in there. Okay, see you in the next video.